In this video, I want to have a look at velocity and acceleration as derivatives. So in our earlier video, we had a look at average velocity and average speed. Average velocity we found by calculating the gradient of the chord on a displacement time graph. But instead of looking at the average velocity, we want to be able to find an instantaneous velocity. So the velocity of a particle at a specific point, not the average over a particular region. So to find the instantaneous velocity, instead of looking at the gradient of a chord, we're now going to start looking at the gradient of the tangent at that point. So we know that to find the gradient of the tangent of a curve, we can find the derivative of that curve at the point. So the instantaneous velocity is the derivative of the displacement with respect to time. So if our displacement is x, then our velocity v, we can differentiate x with respect to t. So this is one notation for the velocity. The other is this here. So the velocity is the derivative of x, which we can write as x with a dot above it. The other thing we need to know is that if an object is not moving, we say that it is at rest, or that velocity is equal to 0. So we know that velocity and speed are related. So instantaneous speed is going to be the absolute value of the velocity. So we'll find the velocity first and then take the absolute value. And the reason we do that is that displacement and velocity are what we call vector quantities. So they have a magnitude or a size and a direction. So they can be positive, negative, or 0. On the other hand, we've got distance and speed, and they're what are called scalar quantities. So they only have a magnitude or a size. They don't have a direction. So that means they can't ever be negative values. So if we have a look at an example, think back to our last video when we had the example of a ball being thrown straight up and then falling back down to its original position. And we're given this equation of its motion. So this question is asking us to use that same equation and determine the instantaneous velocity at t equals 2, t equals 4, and t equals 7. So if this is our displacement, then we're going to expand that out. So we'd have x equals 40t minus 5t squared. So that's our displacement. To find velocity, we're going to differentiate that. So our velocity would be 40 minus 10t. So velocity, we could write it as v, or if we wanted to, we could write it as x dot, or we could write it as dx dt. They all mean exactly the same thing, and it's up to you which notation you use, but you need to recognize that different notations might be used in different questions. Okay, so this is the equation for our velocity, but we want the velocity at these three specific points. So at t equals 2, our velocity would be equal to 40 minus 10 times 2, so 40 minus 20, which would be 20 meters per second. At t equals 4, so at 4 seconds, we're going to have the velocity equal to 40 minus 10 times 4, which would just give us 0 meters per second. And at t equals 7, we'd have the velocity equals 40 minus 10 times 7. So that would give us minus 30 meters per second. So that's answered the first half of our question to find the instantaneous velocity, but we also want the speed. So for each of these, the speed would be the absolute value. The absolute value of 20 is just 20 meters per second. The absolute value of 0 is just 0. So those two stay the same. But this last one, the instantaneous speed there would be the absolute value of minus 30, which will just be 30 meters per second. The next thing we need to look at is stationary points. So we say that a particle is stationary when its velocity is 0. So that means it's when its first derivative is equal to 0. And that's actually where the term stationary point comes from in all the calculus work that we've been doing so far. So let's have a look at a problem involving stationary points. So our question says we've got a particle moving so that its distance from the origin is given by this equation here. Then it's got two parts. It asks us to find the times when the particle is stationary and to find its displacement at those times. So to find when it's stationary, we're going to have to find the velocity and set the velocity equal to 0. So if this is our displacement, then for part A, our velocity is going to be the derivative of this. So that would give us t squared minus 8t plus 12. Now we want to set that equal to 0. So 0 equals t squared minus 8t plus 12. And then we're going to solve that. So we can factorize it. So we have t, two things that multiply together to give 12 and add to give minus 8 would be minus 2 and minus 6. So that means our 2 times will be t equals 2 seconds and t equals 6 seconds. So that's part A. Part B asks us then to find its displacement at those times. So at t equals 2 seconds, we're going to substitute t equals 2 into our original displacement formula equation. So substituting 2 into all of those and working through the whole thing, we would end up with 5 2/3 meters. Given that this is in meters and seconds, it doesn't actually tell us that in the question, I've just assumed that. And then we'd do the same thing at t equals 6 seconds. We'd substitute 6 into this equation up here, and we would end up with minus 5 meters. The last thing we need to have a look at is acceleration. So a particle is accelerating if the velocity is changing. So the acceleration is the rate at which the velocity is changing. So that means if it's the rate that the velocity is changing over time, that means acceleration is going to be the derivative of the velocity with respect to time. So we could write it as dv dt, or we could write it as v dot. But we could also write it as this. So we already know that the velocity is the derivative of the displacement. So that means that if acceleration is the derivative of velocity, then we could also write acceleration as the second derivative of the displacement. So d squared x dx squared, or x with 2 dots above it to represent the second derivative. So let's have a look at an example of that. So if we look at the same equation as we did in our last example, so we've got a particle moving with this equation here. This question asks us to determine when the acceleration is equal to 0 and the displacement at that time. So the acceleration, we need to find the second derivative. So our first derivative we already figured out in the last question was t squared minus 8t plus 12. So then we can differentiate again. Oops. So you could be writing these again as v and a if you'd like, it's up to you. If we differentiate that again, we'd have 2t minus 8. Now we want when the acceleration is equal to 0, so when the x double dot is equal to 0. So we're going to put 0 equals 2t minus 8, which is going to mean that 2t is equal to 8 and t is equal to 4. So acceleration is going to be equal to 0 at 4 seconds. But we also want to find the displacement at that time. So at t equals 4, the displacement, we'd substitute 4 into this whole thing, and it would work out to be 1/3 of a meter. So that's happening at 4 seconds, and the displacement is 1/3 of a meter. So that's having a look at velocity and acceleration as derivatives.